Alright, in this video we're going to talk about how to partition the sum of squares using matrices. And we've already shown how to partition the sum of squares when we have basically a simple linear regression model and we have basically these I, Y, I. So we're just going to use that, but instead we're going to use matrices to kind of represent the exact same thing. Alright, so remember what our simple linear regression model looked like when we have basically these little subscript i's. So we have our outcome yi equals beta naught plus beta 1, which is our slope, times x sub I plus epsilon sub I. And we would say that goes for I equals 1 to n. Right? And if we rewrite this model using matrix notation, we have a vector of y's. Okay, so this is an n by 1 vector. This equals x, which is our design matrix. Okay, the first column is all 1s and the second column is all of our x's, times beta, which is our model parameters, beta naught and beta 1, plus epsilon, which is an n by 1 vector of model error terms. Okay. And previously, when we had broken out our sum of squares, we said the sum of squares total equals the sum of squares regression plus the sum of squares residual. All right, where we've already shown that this is the sum of yi minus y bar squared, that this equals the regression sum of squares is the yi hat, right, minus y bar squared plus the sum of squares of the residuals, which is the sum of yi minus yi hat squared. So we've already shown this relationship. Okay, and what we're going to do in this video is basically we're going to show this relationship, but instead of using these sums, we're going to show how to write it using matrices. Okay, so starting with the sum of squares total. Let's start with the sum of squares total. So the sum of squares total is the sum of yi minus y bar squared. Okay, so we want to represent this using matrices. So let's go ahead and let's go ahead and FOIL this so that we can simplify this. So we have the sum of yi squared minus 2 times y bar times yi plus y bar squared. Right? What I've done is I basically have FOILed this guy out. Okay, so now let's bring in our sum. So the sum goes from I equals 1 to n. Okay, so we have the sum of yi squared minus, now these guys don't involve I, so they can kind of be pulled out of the sum. Okay, and then this last term doesn't involve an I at all, so when you sum it up n times, you're just going to get n of them. Okay, next let me go ahead and write my y, let's go ahead and write this y bar using that sum of yi. So let's go ahead and write that. So this equals the sum of yi squared minus 2 times, okay, what is y bar? It is the sum of yi divided by n, right? That's what y bar is by definition. That's what a sample mean is. It's the sum of the values divided by the sample size times yi plus n. All right, then I have the sum of yi divided by n squared, right? And of course I can bring that square into both the numerator and denominator, so let me go ahead and write it like that. So I would have the sum of yi squared divided by n squared. Okay, and notice that one of these n's cancel, all right? And also notice that this guy is being multiplied by itself, so that's basically the sum of yi squared. So let me write that like that. So I have the sum of yi squared minus 2 divided by n times the sum of yi squared, okay, plus the sum of yi squared, and I still have 1n on the denominator, so divided by n. Actually, let me, instead of writing that 2 divided by n, let me move that n here. Okay, it's the same thing, but now it's really clear that this guy is exactly the same as this guy, so they're like terms, so I can combine like terms, and I'm left with the sum of yi squared minus, now it's 2 of them, and then this plus 1 of them, so that leaves us with one of them being minus, okay, divided by n. Okay, so now I can write this using matrices. And how do I do it? Well, the sum of yi squared is just y prime, or y transpose y, right? Where y is, you know, an n by 1 vector, right? So y transpose is 1 by n, and then y is n by 1, so you're left with a scalar, which is just the sum of all their squares. Okay, then minus 1 over n, okay, y transpose j times y. Okay, and I know this is a little tricky, so what's going on here? This j is a matrix of all ones, okay, and it's an n by n matrix of ones. So we can, let me go off to the side and kind of show what is j. So j is a matrix, let me go ahead and write that, is an n by n matrix of ones. Okay, J is an n by n matrix of ones. So for example, suppose n equals 2. Then 1 over n y transpose j times y would be 1 over 2. Okay, y transpose would be y1 and then y2. And j would be 1, 1, 1, 1. And y would be y1, y2. Right? And so we can do some matrix multiplication here. Let's see what we have. 1/2. So we'd have y1 times 1 plus y2 times 1. So y1 plus y2 basically. That's the first element. Then the second element would be y1 times 1 plus y2 times 1. Okay, so that's the second element. Okay, times y1, y2. Okay, then what do I have here? Actually, let me use a different color here for these guys so that it's nice and clear what I'm about to do. So then I have, when I multiply this, I have this guy times that guy. Okay, so this guy times this y1. And then you add that to this guy times that guy. Okay, times y2. And notice that these guys are like terms, so they can be pulled out. And I'm left with y1 plus y2 times y1 plus y2. Right? And notice that these guys are exactly the same. So this is, of course, y1 plus y2 squared. Right? Which is, of course, the sum from I equals 1 to 2 of yi squared, which is exactly what I wanted, right? So you see this j, it's kind of like a trick that it works, okay? So you can convince yourself that it works, and it's a way of writing this, the sum that's being squared, okay? All right, so there you have it. This is our sum of squares total using matrix notation. Okay. Next, let's talk about the sum of squares residual. So next, let's talk about the sum of squares residual, which is the sum of our residuals squared. So yi minus yi hat squared, right? And we know that these guys are the residuals squared. Right, and so, you know, right away I can write this using matrix notation as E transpose E, where E is a vector, an n by 1 vector of all of my residuals. Okay. Now E, so let me maybe do a sidebar here. E is just a vector of all of my residuals. This is Y minus Y hat, right, where these are vectors. So this is Y minus X times B, right? Y hat is X times our least squares estimator B. Okay, so let me go ahead and write this out. So instead of writing E transpose E, let me write Y minus X times B transpose times Y minus X times B. Okay, so that's E transpose times E, right? And let me go ahead and distribute that transpose. So what do I am left with here? I have Y transpose minus B transpose X transpose times Y minus X times B, right? And let's see what happens here when we go ahead and distribute this. So I'll have Y transpose Y, right? That's the first terms being multiplied by each other. Then Y transpose times this guy back here. So minus Y transpose X times B, okay? Then this guy times that guy. So that's minus B transpose X transpose times Y. And then the last guys being multiplied by each other. That minus and a minus makes a plus. B transpose X times B. Okay, these guys are the same. So I can go ahead and write them a little bit differently. Let me go ahead and write them as minus 2 times B transpose X transpose Y. Right, so they're the same thing, so I just kind of rearranged, so I'm using this notation here, right? Okay, now this guy, remember what is B? B equals X transpose X inverse times X transpose Y. Right, by definition, right, we've derived this previously. So let me plug this in for this B here. Okay, so I'm going to have B transpose X, and let's plug in that B there. X transpose X inverse X transpose Y. Right, and so notice that this guy is the same as this guy, and then this one is inverted. So when you multiply them by each other, you get the index matrix I, right? So that's very nice. They kind of cancel each other. So let's see what I'm left with. I'm left with Y transpose Y minus 2 B transpose X transpose Y plus B transpose, these guys cancel, and I still have that X transpose Y at the end. Very nice. You notice that these are like terms. Right? So this is minus 2 of them, and this is plus 1 of them. So it comes down to Y transpose Y minus 1 of them. B transpose X transpose Y. And there we have it. This is our sum of squares residual written in matrix notation. Okay. So lastly, we have our sum of squares regression. Right? So let me go ahead and write out sum of squares total equals sum of squares regression plus sum of squares residual, right? And we've already shown that the sum of squares total is Y transpose Y minus 1 over n Y transpose J times Y. Sum of squares regression, we don't know yet. And sum of squares residual is Y transpose Y minus B transpose X transpose Y. Okay, so I can basically use algebra and solve for sum of squares regression. So let's go ahead and subtract this guy from both sides of the equation. And when I do that, so actually let me go ahead and just write it like this. All right, so I'm going to minus Y transpose Y from both sides. And then I'm going to add B transpose X transpose Y to both sides. All right, and these guys will cancel. And what I'll be left with is this positive B transpose X transpose Y, and then this minus 1 over N Y transpose J times Y. And that is our SS regression. Okay, so you kind of just use algebra to get to our SS regression. Right, so there you have it. We have written our sum of squares, total, residuals, and regression, all using matrix notation.